I am a software engineer, a performance and scalability engineer at WhatsApp. What is WhatsApp? I think everyone kind of is aware about. We have different platforms like Android, iPhone, Windows Phone, and Kaios, that's Geophone and other things. We have web client and native clients, and we have more than 1.5 billion people sending messages at least once a month. We also have a lot of various WhatsApp business products, and also that means we have thousands of servers to maintain. What it means? That's an interesting story. We do have testing. It's pretty good. It can be improved, but it's pretty good. Still, when we run some code, either on a laptop or on a development server, there may be a tiny, tiny little bug that may eventually slip, so we can't really see it. Then we deployed some code to a server. Well, it's okay, but something that we missed may eventually fire on the server. If we deploy it on a larger scale, then there's basically more things happening, and if we deploy it to a rack or some set of servers, we will surely see more bugs, crashes, and issues. And as soon as we do it at a large scale, that will be a whole abundance of different things crawling around, because testing never replaces troubleshooting. What's the problem with that? Because unlike your laptop, the world is not controlled by either you or administrator of a single thing. We have so many different moving pieces. All servers may have various differences in hardware. The operating system could be either Linux or FreeBSD, or maybe, I don't know, Erlang doesn't work on VxWorks anymore since OTP R22, but it used to, and well, we never used it, but I see how it could work. So there could be different kernel versions, shared libraries, there could be different services running on these servers. Even the application components, the stuff that we deploy, could be just different. So there are a lot of moving pieces. And if something wrong happens, we need to have a workflow that shows us what do we do, and that kind of explains what we should do if something breaks, something unexpected, something that we haven't tested for. The workflow looks pretty simple. First, we need to detect the problem. We need to actually understand that the problem is there, that it really happened. It is happening right now. Then the second step would be to confirm that what we are seeing is actually a problem, because it may not be. Then we need to analyze and find what causes the problem. And after that, we need to find out how to fix the problem and actually mitigate it, or do something, maybe forget about the problem, who knows. After that, there's a verification steps that says, yes, nothing is broken and the problem has been really fixed. And the last and the very unenjoyable piece is actually documenting the whole process and ensuring that that it does not happen again in some sense. But let's start with the detection. How do we detect issues? We have monitoring, and that's a pretty good one. We monitor on all levels that we can think about. Starting with hardware, we do check things like hardware health. For example, like problems with memory sticks missing, like CPU overheating, or even the power supply being flaky. Yes, these things are monitored, these are detected, and there is some preventative therapy coming for these machines. So we migrate our services off these machines and basically replace it. We also monitor operating system and kernel and system applications. How does it work? Well, apart from traditional monitoring, we also log everything happening on these machines. It's basically a large log of ATOP data and other data. So what is ATOP? It's just a Linux application that may do snapshots of your running processes and things like that every now and then, or every second, like we like to have. We also monitor the Erlang beam itself, the virtual machine, and do that from both points of view. From the internals, we monitor ports, processes, and various memory metrics and stuff like that. And we monitor that externally. We actually see how much resident size is currently taken by Beam. What's the CPU there, and like other things like that. But we also monitor application level metrics. Like to name a few, say, we do know how many messages are coming through our systems, and we do know how many users are currently connected. Well, these may not be the very precise numbers, but at least we have a vague understanding of what's happening here. And if something wrong happens, we are getting alerted. Or we can just randomly look at dashboards and detect, hey, this is a problem, this dashboard looks different, and there is definitely something happening there. And if something is happening there, what do we need to do? We do need to confirm the problem. We do need to understand that it is actually a problem. Because there were soccer matches that were looking like an interesting thing on a graph. When there is a goal scored, there was a like 5x spike. And while in theory, yes, we have alerting and monitoring all over our heads, it's actually not a problem. It's just a football match, which is kind of a good problem to have. Some problems may be caused by just user base growth, something that, I mean, we've been kind of expecting, but just as William Gates III was thinking that 64 kilobytes is enough for everyone, we may eventually think about that too. Say, for example, default Erlang, million atoms should be enough for everyone, right? Yeah. And this is exactly what may happen if we think that something is definitely enough and then it's not enough. We still need to monitor that. And if we see that it has happened, then we need to confirm that it has happened because we did something wrong, or just because it was organic, and then we need just to adjust alerting thresholds. But then, after we realized, yes, it's definitely a problem, and we need to do something to it, to fix it somehow. So we need to analyze. We need to collect evidences. So this is a very important step. Yes, we do have log files. Yes, we do have different storages for every kind of information. We store pretty much everything, but things like high-resolution counters are not worth to store for every single server, every single application, every single thing, just because it takes so much space that we shouldn't. I mean, there is just no point in keeping them forever. But if the problem happens, yes, we need to preserve it in a cool, dry place somehow. Or we may want to have some additional data that we just get on demand. And for that, we have a kind of a framework that lets us a quick, really quick, and sometimes really informative glance into what's happening within the Beam or our application. We have a framework that is called internally, but I guess that name will get wider somehow and get to broader audience, eCTL framework, like eControl. It is inspired by eJabber DCTL, and the roots coming from there, but we have extended this to handle a lot of different scenarios. Here, from the bash script, we just enter eCTL PI 54, and then we get a large amount of information. What that means, we just asked Erlang to tell us about the process 54 on the node, which happened to be inetDB. Why I thought that it would be important? Because it happened to us that the process with this number has been reporting a huge amount of CPU consumption, and we were interested, well, what's happening in there? So here we can clearly see that the message queue length for that process for inetDB is, that's a large one, some 112,300, oh, a lot, anyway. So this is how we can just take a quick glance into what's happening within our application or Beam. And the eCTL framework is pretty extensive, so we can do a lot of things with that. For example, we can do hot code loading, and 3 talks ago, Richard Carlson was telling us about how they do hot code loading, and frankly, it's the way we do hot code loading too. So we can just basically specify the order, the load order of modules, and then specify -a, meaning that yes, then we just load the rest of modules. And this is all in our ECTL framework. It is pretty extensive. And the good thing is, at some point, WhatsApp is planning to actually release it to open public, to you. How does it work? That's pretty simple. So we have a node, a server, a beam running somewhere on the server. We may SSH to that server and run a hidden node, name it somehow, connect, join the cluster, and basically send Erlang distribution messages. Simple, but working solution. Sometimes we need even better way to communicate with nodes. For example, we may have 1,000 servers in a single cluster, and we don't really want to SSH to every single machine and do that command. So we can send a command to one node, and then it will communicate with the rest of the nodes and send them messages, ask them to do something, or maybe perform some investigation things. Why it may be necessary? Because it happens that joining the cluster doesn't work because of different bugs in Erlang and OTP. It happened to us, and that's a part of a troubleshooting that we came with. OK, let me tell an interesting story about what has been happening once. It happened that one of the machines that we've been running did not want to react to ECTL commands because the hidden node was not able to enter the cluster. So what I did, I started that introspection thing, and I tried to create a node and manually enter a cluster, and it didn't work. So what I did, I looked into source code, into OTP source code. I looked how it works, how cluster join event is getting processed, and then I realized I want to try that, and I want to try these functions that are in the OTP files. I want to call them directly from the shell. Unfortunately, I was not able to do that because these functions were private. They were not exported from the OTP. OK. And we implemented PowerShell. What is that? That's just basically an extension to Erlang shell that lets you call an exported function. This is the one that I wanted to run, just because the dist-util generate challenge was somehow weird. Well, it wasn't really weird. It was just hanging because there were other things and other problems happening within OTP. But I wasn't able to call it because it's not exported. With the PowerShell, evaluate the function, and I get a number, and it works. So that, OK, nice. The good thing about this library that it has been already open sourced. You can just clone it or use it. It's on the GitHub. And for just WhatsApp audience, I have baked that into the shell, the Erlang shell itself. So the calls are even easier. So I can enable debugging unexported functions and then just run them this way. This is convenient, but that is a patch to OTP. If Erlang accepts this, then that's fine. I'm happy to provide that. If not, then you have PowerShell. How does it work? That's simple. Well, if Beam file is compiled with the debug information plugged in, what do? We just take the chunk that contains debugging information, basically get the abstract syntax tree, and evaluate it just the way shell does. Simple, but effective. But what happens if we need some other information that's not necessarily running some simple troubleshooting? We need real-time monitoring data. And we've got that too. Well, we have, pretty much the same way as ECTL, we have another utility that can read the counters and things from our application and just basically print them to console. So we can see, the red color here is what I made. The actual print is black and white. But, well, we are just used to looking at the sum columns and realizing, hey, the scalar utilization of 92% is kind of high and not what we expect there. What is scalar utilization? Well, let's just talk about the computing resources. We have three main classes, which are CPU, RAM, and network. There are probably some other resources, but we care more about these three. What is CPU. In Erlang, CPU is really different to what we are used to for any other languages. Because for Erlang, it is all about scalars. And to be precise, mostly about normal scalars. These are things that are actually running our Erlang code. So how it generally works. What is a scalar? It's a thread, an operating system thread, or lightweight is fiber, or whatever the abstraction is in a specific operating system. And it executes your code. Emulator stage means that it does some beam instructions. Ets means it tries to do something with an ets table. GC, that's a garbage collection, or maybe major garbage collection if necessary. There are some BIF calls, NIF calls, and also busy-wait things. But there is a way to take a look into Beam and find out what's happening within either a single scalar or many of them. And that's called Microstate Accounting. I'm promoting this feature pretty much everywhere because it's super nice and super convenient, and it shows you exactly what's happening with your system. This is how it looks when everything is kind of normal or even underloaded, just because we have a lot of scalars actually sleeping and doing nothing. That means we should have some free CPU time, and we can increase the load on this machine. We still have at least 23% of normal scaling time. But sometimes things go wrong. And if we see that there is a problem with an ets table, it's generally ets table contention when there are too many processes accessing the same table, writing and reading data from there. This is how it looks. And then we know that, yes, that's the problem. But sometimes we see this, and that means there is most likely lock contention somewhere within NIF function. And it happened to us too, and the NIF function was actually one of the functions that's called by SSL when doing crypto. We solved the problem, but this is how we find it. This is how we analyze it. This is how we detect what to look at and what to try to. Sometimes we even see the garbage collection loops taking too much time, but that's so rare that, well, it's still worth mentioning though. And it's good that we have Microstate Accounting built into Beam. And to get more extra flags, you will have to build your specific Erlang OTP distribution, because traditional ones don't have that much of an introspection. For memory, probably everyone knows about the Recon library built by Fred. We have our own kind of version of that, still inspired by Recon, but it's pretty convenient to have that embedded into our ECTL framework. So basically from shell, we just run a single command and we get the full statistics. That's just half of the statistics because the full one didn't fit the screen. But this is what we see here. So we can see per allocator things. Like if there is a problem, we can basically easily see that, hey, this etsalloc is underutilized. It's allocated 18 gigabytes of RAM, and using just 3 of those, that gets us 17% utilization. Why? Because this allocation strategy doesn't really work for that kind of allocation. This is a very recent problem, by the way, and we have a person here in the room who knows what the problem was. We changed the allocation strategy. We changed the allocation strategy, and now we got much better. It's like 3 gigabytes and 2 gigabytes, but then most of that is actually utilized. And it's really convenient that we have these tools to help us to find what's wrong. If we want to debug some memory leaks, for example, these are not really leaks because Erlang shouldn't at least leak the memory by itself, but some processes may have references to some data structures left somewhere in memory, and those can go to the old process heap, and they can be stored there pretty much forever until someone makes a forced garbage collection for that process. And that is exactly what the leak detection thing does. So we just force garbage collection for every single process and then see what happens before and after that. And here we see that we collected more than 1 million of references to some binary, and we just freed up more than 230 megabytes of RAM from a single process. I had to remove process names for legal purposes, reasons, but yeah, this is how it looks in general. What happens if we do even deeper introspection? Well, that's kind of an interesting thing. If we need to dive even deeper into Beam, we use GDB, which is a debugger. And frankly, Erlang is a language, well, the Erlang VM, the Beam, is a virtual machine that is supposed to do soft real-time scheduling, which means that we cannot and shall never interrupt scheduling for anything longer than 1 millisecond. But frankly, we don't have to. GDB actually supports so-called asynchronous mode and background execution mode. So we don't really have to interrupt it. We can run GDB on a production node and debug actually Beam that is running and serving our customers. We just need to do it really carefully and don't stop it for any longer than 1 millisecond. But even during that time, what we can do, if we really need to find out something is wrong happening with the scheduler, it's just a very simple example, but in fact you can do a lot more. You can just switch to any thread, you can just get any statistics you like, you can do pretty much everything in there. Just be careful and don't ruin the Beam. Even if that is not enough, then the heavy artillery comes into play. We change source code because, well, we can see that there is some lock contention happening in NIFs, but what is the actual lock that gets contended? Well, in that case, we have to modify the source file, we have to recompile the virtual machine if necessary, and then we see, yeah, the problem was in crypto RSA lock because there are some interesting thing how OpenSSL handles RSA keys due to different, again, problems there. Okay, so let's assume that we finally found what has been the problem there, and we are now able to get to the next step, to mitigate the problem, or at least try to do that. What's the problem with this? We want to iterate quickly. And this means sometimes we have to prototype in production. We can just SSH to the production node. We have all our source code there on a production node. We can change it right there, we can compile it right there, and then we hotload exactly the way Richard was telling about us, about that in like 3 talks ago. This is what we do. Sometimes it's not necessarily the best practice to do, but for firefighting and troubleshooting, it's probably one of the fastest way and one of the fastest turnarounds possible. Again, we just need to be really, really, really careful. And we need to remember, it does not replace testing. You can do prototyping, but you will still have to write tests after you realize that, hey, yeah, that prototype works. And unfortunately, this prototyping has a very immediate effect on our users. If we crash a server or the whole cluster, then yes, WhatsApp goes down, which frankly didn't happen last few days. I'm kidding, but yeah. How do we ensure that actually it is not that scary to do anything in production? We have built a reliability layer, which is a very important part of our life. So what happens when a message comes to WhatsApp server? We actually spawn a copy of that message and keep it in some kind of reliability net. So if a server goes down and dies, after some time, there is an alarm clock telling us, hey, we got to resend this message through another server. And this way, even if a not so really careful developer breaks one server down, it's probably kind of okay. At least we are not losing any messages, any user data, and the developer can at least to be warned about getting more careful next time. All right, so after we prototype the issue, prototype the fix, after we created some beta fix, we need to actually mitigate the problem. And there is kind of a pyramid that we use to assess what level of interaction we want to have. So the very top thing is configuration. If the problem can be fixed by changing the configuration, is generally the smallest fix possible, and then we do that. If it's not enough and we need to change the application code, then yes, we have to do that. If there is a problem within OTP code itself, then yes, that's the level, or for Beam, or maybe for container setting, or maybe even for host setting, because sometimes we were able to discover a really interesting problem, like a missing resistor on the motherboard, which was making Beam crazy just because Beam was spiky at scalar utilization. That's an interesting problem. You can ask Quanta why they release their biases every 3 months or so. But every time we make a fix, we have to define a change level. And when we know the change level, we need to talk to the teams, or at least make an announcement that, hey, we are going to change this, and you may be affected by this. After that, and when we have some kind of agreement between these teams, we need to execute the plan and test. If we make a change on the application level, we need to test what happens if we restart any of the underlying levels. Because hot code loading is awesome, but it doesn't test your node restart. And also, we always try to roll things slowly. Again, it's totally in line with what Richard was telling. Yes, first we start with a single node deploy, because that way we will see one tiny bug. Then we deploy to a range, or maybe multiple nodes in a single data center. Then we see more bugs, and if we see that, then yes, we re-roll the thing. We can optionally roll it to even more nodes, and eventually we get to full-scale deployment. That's kind of a slow roll mechanism that lets us to catch problems before they go to all servers in our environment. And the last but really important step is the documentation of what happened, what steps were taken, how we fixed that, and how we avoid that in the future. I always say that test case is good as documentation, because we can just test anytime we like. And the tests generally stay up to date. They serve as a contract, or even they present some kind of an interface. The tests may catch or may not catch regressions, but sometimes tests are not possible because you cannot test a football game, for example. Sometimes they're just not feasible because creating a test for some feature may be like 10 times more expensive than, I don't know, just creating another WhatsApp. And that means the test case does not replace monitoring and evidence collection. So if we cannot create an absolutely covering everything test, then we need to improve monitoring. And next time, when the problem happens, we are really aware of what's happening and how we fix it and how we fixed it last time. So that's basically all, but I think there may be some questions that I can answer.
Questions? Do you put any requirements on who or what level of experience an engineer has to be able to log into a production node and start playing with it?
Well, first of all, we trust our engineers. And that means there may be some restrictions if they are legally enforced. But if there are no legally enforced restrictions, we trust our engineers.
Yeah, so you mentioned doing a hot code change in production. If that change doesn't work, do you have a rollback strategy?
For testing in production, you mean?
Yeah, if you're logging in a production box and you're swapping in new code, that's what you were doing. That's what I understand, right? And then what if that code doesn't work? What if it has a bug in it? Do you have a way to roll it back?
Yes, well, but not rollback in terms of rollback. Again, as Richard said, in Erlang there is no rollback. There is it's always roll forward when you load some new code. So how it works, if we see that the code that we have just hot loaded is breaking something or causing us real troubles, first that we can do is actually to get the node off production. For example, stop people from coming to the node, or for example, just completely make the node completely leave the cluster, so there is no user traffic coming to the node or from the node. These are basically two major defenses that we have. In most cases, exactly as Richard said, this node will be restarted because there is no reason to try to recover something that went completely wrong. If it's not completely wrong, if it's just some amount of spamming in log files, for example, then it's not a big deal and we can just continue. But if we suspect that we can try to prototype this change without users coming to the node, in that case, we would just do these preventative measures. We would just divert the traffic off the node, and if this problem can be done with, say, just 1% of traffic coming, we will just let 1% of traffic come to the node and just make it as less impactful as possible.
How many Erlang engineers do you currently employ to handle 1.5 billion requests?
Well, I don't think I'm authorized to answer this question, but what I can tell that not all of the engineers are actually doing firefighting and troubleshooting. So these tools are meant to be used only by trained and qualified people, specifically if these things like GDB, because they may potentially disrupt the large amount of things.
What kind of service uptime do you see on your Beam VMs? Like how often do they go down, you know, roughly?
That's actually a very interesting question. 3 weeks ago, I shut down one of the machines that had approximately 748 days of uptime, and the Beam was running from the very beginning of it. The reason I'm telling that is because that node has been still running Beam OTP R16 that has been released in 2011. I don't know how long that Beam has been there, but for most cases, when we used to be within software infrastructure, you can actually find many great talks about that made by Rick Reed and Jamshid Mahdavi in 2012 and 13. Explaining the way we've been running the software infrastructure. So for those nodes, I can easily see them surviving a few years. But Erlang has quite a nice cadence of yearly releases, so I would expect our nodes to restart at least once a year. And if something goes really wrong, well, there is no low limit on that. You can restart a node every 5 seconds if it's broken.
I had a question about the process introspection with the microstate. Is that part of like this kind of EC control utility, or is that something that's open source?
All right, the first is the Microstate Accounting itself. It is a feature of Beam, of the virtual machine. So it is accessible for any languages that is built on Beam. It's like a very extended, I should actually just show a picture because it's quite interesting to see that. So the feature itself is built into virtual machine. Every Erlang normal scaler is an operating system thread that may or may not, if you turn the feature off, account for time that it spends in every single state here. And there could be either 5 states, this is Microstate Accounting with no extra states on, or like 10 or 12 states if you turn the extra accounting on. That has to be done during the Beam compilation stage. So you can just use the Erlang shell, and the module is called MSACC, like Microstate Accounting. The very simple would be just to run MSACC start for 5 seconds, and then do MSACC print, and you will have information printed something like this. But maybe there will be a lot more numbers because it will also print you a per scalar thing. So this does not require any of our frameworks, but it requires at least OTP 20, and I would really recommend to get 21 because there were some issues fixed within those releases.
So if there is, for example, a mismatch between what the operating system says and what you can actually obtain as information from inside the VM, what tools do you rely on to detect that?
Well, to detect that, it's pretty simple. The counters that we collect from the operating system, you can just view them through any operating system supplied thing. Like top can show you how much memory Beam is currently utilizing. And then from within Beam, you can run Erlang memory function that will return you the sum of, basically sum of everything. You can do the math. What if there is a difference between what operating system reports and what Erlang think it is? Then it means there is a problem within the Beam itself, within the virtual machine. And it happened to us, and it can happen to anyone. So what we do in that case, that's the place where GDB comes into play. And that's when we actually see how it is possible to lose, how it is possible to leak some memory that's somehow unaccounted. For that, there's like a set of traditional tools. Like you can use Valgrind, for example. You can run Beam compiled with Valgrind information or any other tools. The only problem is we were not yet able to make it run in production because just this kind of introspection makes it slow, makes it pretty much unusable for any production style of work. And these are completely different debugging technique when we have to either record the load, record the traffic coming to the node and reproduce it, or like think about something else. And by the way, Erlang itself has a very nice set of tracing mechanisms. So in fact, you can record the activities happening within the Beam, within the virtual machine, and then replay it later at some time. This is one of the techniques we are also using for debugging. I didn't mention it here, but it's not, I mean, it's not something that we are going to open source at this very moment.
Question here. Do you guys have any tools for analyzing crash dumps? So for example, if the virtual machine is already crashed and something happened with it, do you have any tools to look at the crash dumps and understand what happened?
Yes, but that's not our tools. Let me promote ETP commands file that is on GitHub, that is not included in the binary Erlang distribution, but if you search for a blog entry from Erlang Solutions that's telling how to analyze crash dumps, and it's a brilliant story about finding out a bug in, I think, NIF or Beam itself. And I actually showed an example of how it looks. So GDB itself is pretty good at looking into crash dumps. I think that's it. Yeah, that's exactly how it would look if it's a crash dump, except for thread and interrupt commands. So ETP schedulers is a part of ETP command suite that you can just download from GitHub. You can source it from your GDB and introspect anything that has been happening just before the crash. You can view all the processes in the system that were running prior to the crash. You can see all the schedulers, states. You can basically introspect everything because it's a crash dump. As for core dumps, that's a completely different thing. And we've been seeing core dumps mostly because the application runs out of memory. And for that, again, Erlang has a very nice core dump viewer application that you can just run on your laptop and simply import the crash information there. Just be aware that if you are planning to use this, just set them up correctly, because by default, Beam tends to drop most of the crash dump just because it doesn't have enough time to write the crash dump.
So you're running different versions of Erlang on different nodes, and I'm assuming if you have to upgrade at some point, do you just take down the whole cluster and upgrade all of it? And also, if one of the old Erlang don't support some of your tools, how do you do the diagnostics on different nodes?
Just 2 weeks ago, I shut down the very last Erlang R16 node. And before that, for longer than 2 years, WhatsApp has been running a mix of Beam and Erlang OTP version, including R16, R20, R21, and a few custom ones. And they have been able to work together with almost no problems. By almost, I mean you were not able to send funds from R16 to R20 and back. But otherwise, it's just the beauty of Erlang retaining backwards compatibility of term to binary for years. And this is how we get away with that. We don't restart clusters, that's it. We can restart just one machine.
I think we have time for one more question.
You mentioned R16. Are those nodes running on FreeBSD, or do you migrate to the new Linux platform that you mentioned on the code mesh?
There is a talk from Code Mesh in London last year when I've been explaining, I think, exactly that. So we've been running a mix of machines. Some of them were FreeBSD with Erlang R16. Some of them were FreeBSD with Erlang R20. Some of them were Linux with Erlang R21. Some of them were Linux with R20. And that mix worked fine. Just kudos to the OTP team maintaining the term to binary compatibility. But in terms of supporting all these tools, yes, I had to support that for all versions of Beam, except for features that just could not be supported, like Microstate Accounting is just missing from R16, so there is no Microstate Accounting. Instead, you get just schedule utilization, which is a very dumbed down version of Microstate Accounting.
Do you plan to continue with this hybrid infrastructure, or do you guys plan to migrate to the Linux servers that are very small that you described on your last talk?
Well, again, I don't think I'm authorized to answer that sort of questions. Hopefully, we can migrate to some, standard infrastructure, but that's something that I cannot tell.
Thank you, Maxime.